Find the traces for the following function when x is 0, when x is 1, when x is -1, when y is 0, and when z is 0. And here we are given the function f of yz is equal to y squared plus 4z squared. So the first thing that I want you to note is this function notation. This f of yz can also represent x. So another way to write our given function is as follows. We can say that this is the function x is equal to y squared plus 4z squared. So we are going to use this given function now to find all of these beautiful traces. So trace number 1, we'll start with some of these x traces. So we are asked to find the trace when x is 0. So because this is x is 0, we can also think about this as the yz trace. This is one of the coordinate traces. So what's going to happen to this function when we let z equal 0? When we have 0 is equal to y squared plus 4z squared. Now, let's see, we could rewrite this a little bit. We could say, well, minus y squared is equal to 4z squared. And is this ever true? Well, this is only true when y equals z equals 0. So we can say this is true if and only if y equals z equals 0. So what is this producing? So this is going to produce some sort of a vertex or a singleton point at the origin. So we're thinking about this is not a curve, but an ordered triplet, a singleton point. We have that this only holds true when x is 0, y is 0, and when z is 0. So here is our first trace, a singleton point at the origin. Now what about when x equals 1? So now we have the equation 1 is equal to y squared plus 4z squared. And hey, we know this one. This is an ellipse. So here is our second trace. We have an ellipse. And we can even make a little, an observation here to ourselves. So a little love note that for all x values, for all real numbers x, such that x is strictly greater than 0, we're going to produce some sort of an ellipse. The trace will be an ellipse. All right, now we have one more x trace to consider. We want to think about what's going on when when x is -1. So we have -1 is equal to y squared plus 4z squared. Is that ever true? No, this is a contradiction. This is false. This is never ever going to be true. Why? Well, y squared plus 4z squared is always positive. This is strictly greater than or equal to 0. So it can never equal -1. So this is something to keep in mind when we go ahead and we'll sketch this graph for fun. So this one's letting us know that there's going to be no traces below when x is 0. So now we can go on and think about the other coordinate traces. Let's think about the case when y is equal to 0. So this is a coordinate trace. This is the xz trace. So let's think, if we let y equal 0, we're going to be left with x is equal to 4z squared. And this is a parabola. We know what this looks like in 2 dimensions. And I haven't done this yet, but it can be also helpful to actually sketch that 2-dimensional graph. So here is our x-axis and our z-axis. this is the x-axis and your z-axis. And we know that the shape of this trace, this two-dimensional curve or cross-section, is a parabola. So this is x is equal to 4z squared. And we have one more trace to go. We want to think about the trace when z is equal to 0. So this is another coordinate trace. This is the xy trace. So thinking about our original function, if we let z equal 0, we're left with x is equal to y squared, which again, we recognize this is a parabola. Woohoo! So we've got enough, and again, the two-dimensional sketch is going to look awfully similar to what we have above, with the exception of the axes are going to change. So for this case, our two-dimensional sketch here is, again, the x-axis. Now this is our y-axis here. But again, we still have our curve looking like a parabola. So this is the two-dimensional trace, the xy trace, x equals y squared. So we've got some important features here. We can actually sketch the surface, no problem. We know we have the yz trace as a singleton point. We know that when x is 1, we have an ellipse. We can also observe that for all x values greater than 0, all of those traces are going to be ellipses. Now we know that the xz trace, when y is 0, is going to be a parabola. And then the xy trace, when z is 0, is also a parabola. So let's put this all together and visualize what the graph of the surface here will look like. So let's sketch the surface. So we want to sketch this in 3 dimensions. So here is the z-axis. We've got the x-axis and our y-axis. All right. So again, when x was 0, we found that singleton point here right at the origin. So here's our vertex, or the singleton point at the origin. Now we also know that when y is 0, we have a parabola. So we'll sketch that one. So here is that parabola in the xz plane. So this is your xz trace. And we also observe that when z is 0, this trace, the xy trace, is also a parabola. And so let's sketch this one. So here is our the xy trace, which is another parabola. And now keep in mind here, in addition to these two traces, we evaluated traces when x was greater than 0. So specifically at 1, and we noticed that, or we were able to determine that this trace is an ellipse. So here is an ellipse, we'll say where x is 1, and then we have these same type of ellipses for any x value that's greater than 1. So look at, just by incorporating or just by identifying these traces, we're able to begin to visualize what this surface is looking like. And so if we really wanted to appreciate, we could shade the surface in a little bit here. So this surface actually has a specific name. This surface that we've drawn is one of the quadratic surfaces which we are about to explore. This is called an elliptic paraboloid. But you can really appreciate the importance of these traces in helping us to identify what the surfaces are going to look like.